In this video I will try to make an optimum second amplifier stage for use in the selective amplifier that I started to build in the previous video, nerds76. First, I'm going to do some experiments on bipolar transistors. I did already in the previous video try a standard noiseless feedback amplifier with wideband transformers, and that did not turn out very well. So here is another alternative. Here noiseless feedback is by this 100 pf capacitor. It is going to produce a phase shift of 90 degrees, and this inductor, 4 turns on an 8 mm diameter core, gives another 90 degrees phase shift, which means there will be 180 degrees, which is negative feedback. And there is a small inductor here, 3 turns, to make this input 50 ohm resistive at 10 MHz. The gain is fairly low, but my interest is to find a low flicker noise, and of course also a low noise at wide separations, means a low noise figure. So a first test is with these component values, 24 milliamps with 82 ohms on the emitter, and I feed it with 12.5 volts on the collector. And the base voltage divider 430 ohms and 120 ohms. So there is a fairly low voltage on the base. Here is what it looks like. It's 10 MHz, so very uncritical, except for the feedback capacitor, which has to be tight on the transistor, because otherwise there will be oscillations in the VHF range. Here is the frequency response, 46 ohms on the input, close to resistive, and the gain 6.4 decibels. The phase noise at 50 Hz is minus 130 on Linrad with the interferometer, and 50 Hz, that's where the spur is. And this is phase noise, and here is the amplitude noise. It is minus 131, so it's fairly similar. I can have both of them at the same time also. At a wide range, the phase noise is stronger than the amplitude noise by 2 decibels, 141 and 143 minus dBc respectively. There is a lot of flicker noise, obviously. I want this to be something like 15 decibels better. The mechanism may be a noise current into the base, causing the gain to vary, or maybe the output capacitance. Well, also varying gain means varying feedback, and that might affect the phase. I don't know really, but what I can try is I put a capacitor here, 470 microfarads. Somewhat unexpectedly, the phase noise is stronger now, 128.5, while the amplitude noise is weaker, minus 133.5. So this capacitor on the base is no good. Without it, phase noise is about 1.5 dB better on all frequencies, while the amplitude noise is worse. But I don't need to improve the amplitude noise, I want the good phase noise. I also tried to increase the emitter resistor, keeping the same current by increasing this resistor and that resistor. So I have 8 volts here and 20 volts here. So it's nearly the same collector-emitter voltage. It has increased from 10 to 12 volts. But the phase noise I see is no better. It's actually a little bit worse than I saw originally. Here. 50 Hertz minus 130, now minus 127.5. And probably because the collector-emitter voltage is a bit larger. I don't know, really. It seems the idea of using noiseless feedback with a capacitor like this is not a good idea with bipolar transistors. It works well with J310 junction FETs, but this doesn't seem promising at all. I'm going to check the system. It is now more than 4 months since I made what you have seen so far in this video, and I'm going to look at sideband noise of amplifiers to use as the second stage amplifier. So first I'm testing my equipment. Oscillators have been running for 4 months and they are aging and maybe getting better or maybe not so. Anyway, this is the configuration I have right now. The Wenzel oscillator plus 13 dBm, 21 dB attenuation and a bandpass filter. Then there comes the interferometer, and at this time I have no device here, it's just open, and this is set for 4 decibels of attenuation here, and there is a little attenuation here also, and this is set to 0 dB. So what I'm looking at is the signal passing through like this into an hybrid from where I can get the sum. Now, since there is nothing here, this is just splitting the signal into 2 halves. One goes into a 9 dB coupler, where I get a signal that is proportional to the signal that I'm sending into the analyzing system, which is the hybrid and the 2-channel receiver and then a sound card with Linrad. And the difference signal, well, at this time it's not a difference signal. Half of it goes here and half of it goes here, and I'm not interested in what comes on the oscilloscopes at this time. I just want to look at the signal when it goes through like this. The system has been running for 44 hours now, nearly 2 days. And the sideband noise at 50 Hz offset is minus 161 dBc per Hertz. At 20 Hz I see minus 153, and at 10 Hz here, minus 146. And at 5 Hz, where the mouse is now, I have minus 137. This is what I see when I look at a wider frequency range, and as you can see, the real part of the correlation spectrum, the sideband noise, is negative, means blue on the screen here, and the imaginary part is equal in size to the real part. So what I see here at minus 172 is not a property of the oscillator. It is my test system that is good enough for this. But below about 100 Hertz, then I have a gain from the correlation spectrum, from using the correlation, that is 22 dB, and that is a little bit on the high side, but at 50 Hertz I can trust the result I'm seeing, and at 100 Hertz I see minus 166, and that is perhaps also a reasonably reliable result. I have set this attenuator to 0, and then I have reduced the gain of this two-channel receiver by about 20 dB, 21 dB. And then I do the measurement again. As expected, I don't see much difference. It was at 50 Hertz minus 161 before, and that's here, which means here. And it's a little bit hard to say, but the distance from here to the orthogonal channel, the imaginary part, is very small. So there is some noise contribution. At 20 Hertz, minus 153. That's here, and 20 Hertz is here, so pretty much the same. 10 Hertz, minus 146. 146, that's here, and 10 Hertz, that's here. And finally 5 Hertz, minus 137, here. So there isn't any difference, and there shouldn't have been either. This is now the device under test. Just nothing. BNC female to BNC female. I have the full gain of the two-channel receiver, and I start by setting this stepped attenuator to 30 decibels attenuation, and then I note the level on the oscilloscope here. And when doing so, I have this stepped attenuator set to infinite attenuation, so there is nothing coming through here, but the impedances are 50 ohms at both ends of this one. So this way I have the signal level here. That's the carrier level, and it's attenuated by 30 dB. Then I change this to 0 and step this to 0, which means I have signal this way and that way, and I adjust amplitude and phase, so I have the same signal level here. It means now the carrier is suppressed by 30 decibels, and I'm using the phase shifter to make sure that the phase of the carrier is correct. It means that I am on the minimum. And now I can measure the phase noise of some components in the interferometer to see if there is something that isn't quite right. Now, after 17 hours and a half, I can see that the interferometer doesn't add any noise. So I have the same reading as before. 50 Hertz, it was minus 161, and that is here and here. And since I haven't waited long enough, the imaginary part is very close, so that little difference I see can be attributed to that. 20 Hertz, I had before minus 153. 153, that's here. And 20 Hertz here. And 10 Hertz, I had minus 146 here. And finally 5 Hertz, where the mouse is, I had minus 137, and no, the mouse isn't quite there, it's more like this, 137. So far good. I will look at the amplitude noise also, because attenuators and stuff will probably add AM noise rather than phase noise. And it's a bit slow. The transforms don't come in so often because the bandwidth is narrow, because I want to get close to the carrier. So here is the amplitude noise, and I click once more, and now I have amplitude noise at the same time as the phase noise. And as you can see, the amplitude noise is well below the phase noise at close range. At wide range they are equal. And I go back again to the amplitude noise. The imaginary part for the amplitude noise is flat from 5 Hertz all the way up to 75, where I stop this measurement. So now I will start to look at attenuators, because that was what I'm after with this series of measurements. I have added 2 3 dB attenuators now, one in each leg of the interferometer. And then I have adjusted again for 30 dB carrier suppression. Here is amplitude noise and phase noise after 5 minutes. And I saved the previous image. It's here. And I will have to wait quite some time to get the same kind of statistics. But I already see there is a problem with these attenuators. If you look at the AM noise, it's down here. And here it is higher than the phase noise. So if I look at AM noise only, this is phase noise, and here is AM noise, I can clearly see there is amplitude noise that comes from these attenuators, and it should have a 1/f dependence. So I don't have to wait for a very long time to see that these attenuators are not the ones I want to use when studying the flicker noise in amplifiers, because that is likely to also be to a large extent amplitude noise. 20 minutes is more than enough to see the AM noise clearly. At 5 Hertz it is minus 136, and at 10 Hertz it is minus 139. So it is 1/f. The attenuators are of this kind, NAT3 from mini circuits. I have now inserted another kind of 3 dB attenuators. These are CAT3 from mini circuits. These are similar, about 1 decibels better, minus 140 at 10 Hertz. Remember, there is an offset of 30 decibels, so the value is actually minus 170. CAT3 are these ones. I will now try another attenuator. This is 50F006. It is from JFW. Already after 1.5 minutes I can see these are significantly better. These attenuators are good. This is what I see after nearly 3 hours, and what I saved is this. It is without any attenuators in line. So AM noise is here, and it is almost the same. And phase noise, of course, is also the same. Not out here, but that is because I have only been running for a short time. If I look for the phase noise only, it should come. Oh, I need to press the mouse on the spectrum I'm collecting. Here is phase noise, and the imaginary part and the real part are equal in size. And only up here I get a reasonably valid reading for the phase noise. But the AM noise comes here, and here my system is much better, because my local oscillators, they don't have AM noise, they have phase noise. So here I have a good reading for the AM noise, and it is nearly the same as I had here. So these are attenuators I can use when measuring the amplifiers that I'm going to use for the oscillator. This is the stepped attenuator I have been using during these measurements with two identical attenuators. And as you can see, I have set it to 0, so I don't get the noise from this one. I have only used this analog attenuator, which can give me only a couple of tenths of a dB, and it's set for very low attenuation, as I can see on where the knobs are. So now I will use only one of these very good attenuators and set this one to see whether this attenuator, the stepped one of the interferometer, is good enough. So now one of the 6 dB attenuators is the device under test, and of course I had to set this attenuator to 6 dB, and here I have no attenuator anymore. Now it is clear that the variable attenuator, when it's set at 6 dB at least, is equally good as the fixed 6 dB attenuator. Both are from JFW, and here is the new measurement after 2 hours, and here is what I stored before when having no passive attenuator in the interferometer. Sorry, no switchable, only the variable one which uses capacitors to do the attenuation. I am now checking this attenuator set to 3 decibels. It has a label on it, JFW Industries. When I'm checking it against the stepped attenuator of the interferometer, and that one is also from JFW. So it seems they have attenuators that are suited for my purpose. I don't know if they are lower the highest frequency they can take. That is a small guess from my side. But I don't know. Anyway, these are okay, while the ones I have from mini circuits are not. I have decreased the transform N from 15 to 12 here. That means a factor of 8. So transforms run 8 times faster, and that way I get an average that is good enough in about half an hour. And I can read at 10 Hz offset here, minus 148. And with the 30 dB offset, it means minus 178 at 10 Hz. The device under test now is the stepped attenuator. I have set it to 1 dB, all these measurements, but I have used different settings on the fine stepped attenuator in the interferometer. And these values are all reasonably good. There are 2 that deviate slightly. Then I have set all the different settings on the device under test from 1 to 10 decibels and set the coarse stepped attenuator in the interferometer. And here I see things that are not quite what I want. There are settings that give about 5 decibels extra noise, minus 143 here and here and here, and I can see 148 very close. So I will try to find out whether it is the device under test or whether it is the stepped attenuator of the interferometer that isn't quite okay. I have changed the signal source. Rather than just using the vent cell, I have added 6 decibels of gain with a noiseless feedback amplifier, which has fairly low amplitude flicker noise, and then an amplitude limiter that reduces the amplitude to about plus minus 0.6 volts. And then the stepped attenuator, which is now set to 0 or to 35 dB. Here is amplitude noise with different attenuator settings on the device under test and on the interferometer coarse stepped attenuator. And I can find marked with green here which pairs are good. And then I combine what I know is good with different other stuff, and then I can find more about what is good and what is not good. So the stepped attenuator I'm using as the device under test has one bad setting for 8 dB. In the interferometer, the 4 dB attenuator is particularly bad, 10 dB more noisy than the best, which is to not have any attenuator at all. I found also that the analog attenuator, which is a capacitor in series with a resistor, can give me just a little more than 1 dB. So I can get 2 decibels by combining it with the 1 dB step. And this way I can find that the 8 dB attenuator is bad. And of course, combining this 8 dB attenuator with the 1 dB gives me that this is bad, because I know the 9 dB is good from here and here. So the worst case, this one, is at minus 170 dBc per hertz at 10 hertz, because I add the 35 dB offset. Previously, here, I found minus 173 dBc per hertz at 10 hertz offset. But here the signal level is 2.5 dB lower. Now that I know what settings create extra noise from this stepped attenuator, I painted those numbers red so I know what to avoid. And likewise on this attenuator, I have to avoid the 8 dB setting. Knowing that, I have used this interferometer to check the noise of this unit. It is this attenuator. It has 1 dB steps plus an infinite setting, and I can use that instead of this to set the appropriate attenuation through this leg interferometer. I find that the 7 dB setting and the 9 dB setting are much noisier than all the others. The typical result is -142 or -143, but these ones are much more noisy, and even the 6 dB setting is a little bit noisy. Now I know what to avoid in the future. Here is the selective amplifier, for which I want to design a second amplifier stage. You can see more about it in the previous video, nerds76. But before going into the next amplifier stage, I'm going to do a couple of experiments that I didn't do before. First, a big capacitor here, 6,800 microfarads. And let's see what happens when I put such a thing in there. Here is amplitude noise and phase noise. At 10 Hz, I see -121.5 for the phase noise and 119 for the AM noise. The carrier suppression is about 35 decibels. I'm using the interferometer, and I'm saving this on a disk file. Here is what I see with that big capacitor in place, and what I saved before is here. And you can see the white trace, that's amplitude noise, has improved dramatically. At 4 Hz it's about 117 now, and at 4 Hz it was about 109 before, without that capacitor. The phase noise is not much affected, but it is a little and in the right direction. So it's about 1 decibel. So I will mount that capacitor permanently. I have removed this capacitor to disconnect the crystal filter, and I'm still feeding the amplifier through the wideband input here. The result of that is striking. This is what I see, and I will show. Here is what I had when the filter is connected. The yellow trace has gone down extremely much, which is the phase noise, while the amplitude noise has decreased, but not quite as much. And this is at low frequencies. At high frequencies, the amplitude noise hasn't changed, but the phase noise has. I have added a second amplifier stage this way. It's transformer feedback, the emitter current into the transformer, the same transformer as before with the same number of turns here. So I want to have a load with 50 ohms at this point, and that is done by having current feedback from the emitter. There is also a factor of 4 voltage transformation from the collector to the emitter. and a couple of turns extra to bring the voltage up a little bit to make the impedance 50 ohms at this point. Actually, the impedance seen by the transformer at this point is a little bit higher than 50 ohms. I haven't adjusted it quite properly. The sideband noise I see does not look good at all as compared to what I had without this extra amplifier stage. I have saved the screen. It's like this, and you see the phase noise, the yellow curve is down here. But now, with that extra amplifier, it's up here. So there is a dramatic degradation. At 10 Hz now, I can read about minus 117. 117 plus the carrier suppression I have, 35 dB, means that what I see is minus 152 dBc per Hertz. Now, that's not as bad as the impression when comparing it with just the first amplifier stage. Actually, it is better than the best oscillator I have seen. That was minus 151, this NEL 11714A. 10 Hertz, that's here. But I want to go down at least 15 dB from that, if possible. I have reduced the power in the second amplifier stage. That means lower current. And also changed the loading impedance on the collector. The phase noise is now lower, about minus 124 at 10 Hertz. That's minus 159 dBc per Hertz. So it's better, but it's not at all as good as I had with just a single stage. It's here. I have made this resistor and that resistor larger to reduce the current through the transistor. And I have connected a link 47 ohms 100 pf from the emitter to ground, because after changing on the collector side I had VHF oscillations that is killed by this link. The output is now through 300 pf directly from the collector, and there is an inductor 0.82 microhenries from here to here, and a capacitor from here to ground to tune the collector for resonance, with this capacitor to the output where the load is 50 ohms. With this arrangement, I get the correct impedance to load this coil. I am checking with a single turn on this core the phase and amplitude I had when loading properly in this configuration with 50 ohms here. That's how I measured the low noise before. So I have the same phase and amplitude on the collector of this transistor with this arrangement as I had here. And here is what it looks like. It's 10 megahertz. Layout is not critical, except for the VHF oscillations, of course. I put 10,000 microfarads from here to ground to decouple the voltage feeding the second transistor. There is an improvement, but only about 1 dB. Now I see minus 125 for a performance of minus 170 dBc per Hertz. But what I had with only the first amplifier stage, like this, it was about 6 decibels better. That's 4 times better, means that the second stage adds 3 times as much phase noise as the first stage. So I'm not quite happy with this. I have implemented a second amplifier stage like this. 6 units with the same diagram in parallel, with a BF240 grounded base configuration. There are separate emitter resistors for each transistor, because the noise current that generated by each transistor should not be seen by the other transistors. And there are also separate voltage dividers for the base, and that also improves the noise modulation due to the noise current through the transistors. This turns ratio brings the voltage on the output to a level where the transistors are still almost linear. There is about 1/10 of a dB compression here. These 2 capacitors are tuned for the voltage here to become minimum. And this capacitor is tuned for the impedance at this point to become maximum. Here is the noise performance at 10 Hz. Here I see minus 123.5. And if I change the scale, put 0.2 here instead, you can see that the flat noise floor is at minus 137. And this is with the interferometer suppressing the carrier by 35 dB. I have been running the unit at 16.78 volts. This is the attenuator where I can insert 35 dB attenuation, 20, 30, 35. It is Linrod running here. I have calibrated the S meter to show 0. And you can see 0.00. And the new reading here will soon be available. So attenuation is 34.85 dB. I tried the attenuator on the network analyzer also. It is calibrated, shows 0 now, 0.002 or something, varies a little bit with the noise. And here is the attenuator, and I switch in 20, 35. And I can read minus 34.85. That's the same as I saw with Linrod, so I can trust this. I have printed the screen on paper and evaluated at different horizontal scales, so I get reasonably accurate readings. So here are the raw data points I have seen on the spectra, and then I added 34.9 dB to get this column, and plotting on this diagram where I have several good oscillators, these ones, the curve I get is this one. And as you can see, it bends down at close range, and that has to do with the effect of the crystal filter being also in parallel on the source of the first amplifier transistor. It loads selectively, so the proper result has to be a bit higher here, and I have to find the correction for that. But it looks promising, something like 10 decibels better than the best oscillator I have found so far, which is the NEL 1714A, the red curve here. I have disconnected the crystal again, removed the capacitor I had here, So now there is no selective load on the input, means the frequency response is flat over the interesting frequency range. So now I will only see the phase noise from these amplifiers when the input impedance is very high at this point. Before, when the crystal was connected, the impedance was about 50 ohms here on the resonance, which means that this transistor produced noise, of course, but there are also possible other problems. And also, when running in the interferometer, balancing the carrier, I don't balance the noise to the same extent because the carrier is attenuated by the load from the crystal, but the noise is not. And here is what I see. And this is what I have with the crystal in place. And at very close range, below 5 Hz, the difference is very large. But above, let's say 50 Hz, here, the noise is a little bit higher. And the amplitude noise and the phase noise, they are affected in a similar fashion. So, without the crystal, with the crystal. I have reconnected the crystal, but without the capacitor, just a wire here, because I have found in the literature that the DC voltage across the crystal may have some influence on performance. So I will apply a DC voltage at this point at some later time, when the noise studies are completed. I have replaced the Wenzel oscillator by a better one. This is something that I made myself, and it is rather similar to the one I am working with at this time, but it has JFET transistors in it. I placed it on this cable roll because it's heavy and it's standing on foam plastic, and this is to avoid vibrations in the unit. What I see now is a little different. Before it looked like this, and now I have this. And obviously signal to noise ratio wasn't good enough here at 1 Hz before. It is only about 8 dB now, and I have 20,000 averages now. In the old measurement here, this is with AM and phase noise on the same diagram, so I don't show the imaginary part. But this was just 11,000. That's half as many averages. So it is the problem of statistics. The difference isn't very large. But at higher offsets, you can see the imaginary part goes down rapidly. And that the reason is that my local oscillators have far higher sideband noise at close range. So I have to wait for a long time to see the oscillator at close range. Maybe also the use of a better oscillator has some little influence. It looks like maybe half a dB or so, maybe 1. And I will show the combined AM and phase noise now. Here is the combined AM and phase noise with a longer time and a better oscillator. And this is what I saw before. I have been waiting 4 times longer, 48 hours now. Here is what I see. And I compare this with the previous measurement, like this. and there is a small difference. So it is now 47 hours and 12 hours. And here is almost no difference. But at close range, where statistics is not so good, there is a significant difference. So this is what I will print out and evaluate. And also at wider range. The new measurement is not very different. It's nearly the same here, but it is a little bit lower. So there is still a steeper slope here, and then it goes less steep here. But this is not an oscillator, so I don't exactly know why. I will try to find out. I have connected the output of the amplifier to the oscilloscope with a 50 ohm input. And the amplitude I see here is 1.07 volts. And that is 2.85 milliwatts. Plus 4.5 dBm. That is 2.85 milliwatts. And I set my attenuator to 35 dB, means that the signal I get out now will be minus 30.4 dBm. So I connect it to my 2-channel receiver and calibrate Linrad to show minus 30.4 dBm. I'm running now with correlation spectrum enabled, and I've calibrated the S-meter to show minus 30.4 dB. Means now that the zero on the scale is 0 dBm. And I will disconnect the signal. Here is the noise from the amplifier when it has the crystal on the emitter. And as you can see, obviously I haven't had the frequency tuned absolutely correctly. There's a little offset. For this, it shouldn't make any difference for the measurements I'm doing. And I can see the noise floor I have now. It is minus 152.7. And I can check the noise at a separation of 10 Hertz. It is now 0.25. So I click here. And this is 10 Hertz on one side. And I have to wait a little to get the new noise reading. I can see here I have 0.7 decibels of correlation advantage. So the noise is 0.7 dB lower than what I read here. So it is minus 167 160.4 plus 0.6. That is minus 161. And that is dBm per Hertz. Now I'm looking at 200 Hertz offset, and there the noise is minus 163.7 plus 2.5. That is 166.2. So the amplifier noise is significantly lower than the noise I see with the strong signal. So the amplifier noise is here, but at 200 Hertz it is a little bit higher than what I have seen from the sideband noise measurement. I added, of course, 3 dB because the noise I see is AM plus FM when measuring the total noise. I have shifted the frequency to the center of the filter. A very small shift, and I didn't notice any difference in the signal amplitude, maybe 1/10 of a dB or something, but the shape I see on the sideband noise is very different. This is what I see now, and the amplitude noise very close to the carrier is much lower than the phase noise. Previously it looked like this. So amplitude noise is improved and phase noise is degraded. And it is a significant difference, 2 dB or 3 maybe, on the phase noise at a couple of hertz. I have connected an inductor with a very large inductance and a very low capacitance across the crystal DC-wise to this point. That is to ensure that there is no DC voltage across the crystal. And the crystal, it has an equivalent parallel resistance, and that has to be noisy, and that produces a noise voltage across the crystal, which this inductor should remove. Whether that matters or not, I don't know, but it seems to a small extent. Later on I can try to inject a signal here, a sine wave of some frequency, and note how much it is going to modulate. It should cause phase modulation, because putting a DC voltage across the crystal will change the geometry of the crystal, just like an AC voltage will do, but of course to a much smaller extent. The inductor did not make any significant difference, so I could as well have left it out. But what I done now is I tuned the oscillator a little bit to the side of the crystal frequency, and that made a big difference. Here is what I had before, and here is with a slight frequency offset. Here is what I see with an offset signal. At 2 Hz there is a significantly lower level, 2 for about 6 decibels. But already here at 20 Hz the difference is about 1.5 dB, and at 50 Hz I see no difference at all. All the curves are the same at wide separations because it's the noise figure of the amplifier that determines performance. But it's clear that a signal that vibrates the crystal generates noise, and I must assume this noise is produced by the crystal itself. So first I will find out what is the frequency separation I have been using now. To do that I use the network analyzer, input here and output here, and at the same time I send the carrier that I'm using into this input at a fairly low level, attenuated by 40 dB. So the two signals combine here, and I will see on the network analyzer where the zero beat between the two signals is. I set the frequency span to 10 Hz. And I did that already before. And you can see the beat frequency coming closer to 0. Here it is 0. And the peak is here. This means that the offset is 3 Hz. And vertically I am about 1.5 dB from the center frequency for the crystal. So whether it is the offset or the lower level on the crystal that makes the difference in lower close-range noise, I don't know, but I will test by running a 2 dB weaker signal through the amplifier. I have tuned the oscillator to place it at the center of the filter. As you can see here, the place where the 0 beat is also where the peak of the filter is. Here is what I see with the 2 dB lower signal, and compare this is at the full signal level and this is at 80 Hz separation, and the difference is about 2 dB because the noise comes from the noise figure of the amplifier essentially. But when I look at close range, this is at full power, and here is what I see at 2 dB lower signal level. Not much difference. Here is the full power, and here is lower power. That is at 20 Hz. So only at very close range the noise has gone down in proportion to the carrier power. So the problem I see with noise being reduced very much by a small offset is some phenomenon that is not the power level that is seen by the crystal. And I don't know what could be the cause of this. Maybe I can find out later on, maybe not. The noise level I found from the amplifier without any signal. This was here, just measuring the noise floor, and here is what I get from the sideband noise measurement. The error or the difference between these two is 3 decibels, and that looks a little bit like a software problem, so I will check this more carefully. I have attenuated the signal by about 70 decibels and then put amplifiers after the attenuation. This way I get a signal with a high sideband noise. That's the normal noise from the amplifiers that are fed with just a modest signal level. So, as I can see here, the sideband noise is about minus 88 dBc per hertz, and I'm not using the interferometer, it's just this noisy signal. I can change the frequency scale, 0.2, and that gives less noisy signals because points are averaged, and I can read something like 87.8 or so. I have changed the transform size from n equals 14 to n equals 10. That means that collection of statistics runs much faster. And as you can see, it doesn't take a long time, so I will wait for a while to read this with some decimal. As expected, amplitude noise and phase noise are equal. Here, at the high end of this curve, there is an artifact due to a filter in Linrad, so disregard this last piece. The error is a few tenths of a dB as expected. And at lower frequency offsets, there is some noise from the amplifiers, some flicker noise. But at 200 Hz, 300 Hz or so, I have minus 87.8. I have now changed to normal receive mode, but I have not changed anything on the hardware side, and calibrated linear to show 0 for the carrier, 0.01 or 0.03, and the bandwidth is 1 kHz, so the dB hertz shows 30 decibels below. And then I look 200 Hz away, like that. Sorry, I have to go further away, of course, with this wide filter. Now I have set the frequency 1 kHz up. And here I can read the noise floor. Oops. Minus 84.9. With the sideband noise measurement I found minus 87.8, and that was AM noise and phase noise separately. Now I'm looking at the sum, so they should differ by 3 dB. 84 minus 3 is minus 87. So the difference is 1/10 of a dB. So that's within the accuracy of the measurements I'm doing. I haven't read out too carefully on the decimals. So there wasn't a programming error. Just by some unknown reason I found this discrepancy of 3 dB when measuring on the oscillator I am testing. Now it was a little bit difficult because levels are so low, noise levels with that, so I must have made some error. But the calibration of linear is not in error. When doing the measurement that gave me this point, I had calibrated for 0 at 0 dBm. So this point is actually dBm per hertz. But the carrier is 4.5 dBm. So the measurement was actually here. I had planned to compare the value I had with the measurement from a noise figure meter, but I never did that. So I have to move the curve downwards for the noise generated by the amplifier with no carrier present. So crystal noise is even more important than was evident before. In the next video, I will continue towards making an oscillator from this selective amplifier.